Imagine measuring a room. You stretch a perfectly calibrated blue tape measure across the floor, noting the exact distance. To be safe, you grab a flawlessly calibrated red tape measure for the exact same space. But this time, you get a completely different number. The numbers are precise, yet refuse to match. This crisis is the Hubble tension. One expansion measurement yields 73, another yields 67.4. Scaling this gap across billions of light years compounds the error, creating thousands of kilometers of extra distance every second. This gap creates a paradox. A faster expansion rate means the universe is roughly 12.6 billion years old. However, we've mapped specific stars burning for over 13 billion years. The math suggests these stars existed before the universe itself. The presence of these ancient stars suggests that our current models of physics fail to account for the actual history of our universe. A century ago, astronomers lacked a reliable way to gauge cosmic distance. The scientific community was still debating whether the Milky Way galaxy comprised the entire universe, or if there were island universes beyond our own. Edwin Hubble solved this by identifying Cepheid variable stars. These stars pulse at a rate tied directly to their true brightness. By comparing their actual light output to how dim they appeared from Earth, Hubble could mathematically determine their distance. Proving Andromeda sat millions of light years away instantly multiplied the scale of the cosmos, turning a single galaxy into one of billions in an expanding void. This technique became the foundation of the distance ladder. By using these stars to reach nearby galaxies and supernovas to reach distant ones, we can measure the physical expansion of the modern universe rung by rung. Decades of observations from the Hubble Space Telescope solidified this measurement. After studying hundreds of galaxies, the data consistently pointed to an expansion rate of 73. Nobel Prize-winning researchers have spent years refining these calculations, cross-checking the data to eliminate the possibility of human or mechanical error. Every direct observation of the modern universe delivers the same result. Space is stretching at a rapid 73 kilometers per second. A second measurement method ignores modern stars entirely, looking instead at the very beginning of time. This is the cosmic microwave background, or CMB. It is the oldest light in existence, captured shortly after the Big Bang. It serves as a baby picture of the universe, recording the density of the early cosmos before the first stars ever formed. When this early universe data is processed through our standard laws of physics, it predicts that the modern expansion rate should be 67.4. Initially, scientists assumed the stellar observations were flawed. Many suggested that clouds of cosmic dust were obscuring our view of the Cepheid stars, leading to an incorrect distance reading. To test this, NASA deployed a James Webb Space Telescope. Webb sees in infrared, which allows it to peer through dust and verify the stellar distances with absolute clarity. The results confirmed the original Hubble data. Even without the interference of dust, the expansion rate remained at 73. We are now faced with two flawless contradictory truths. We have an observation of the present and a prediction from the past that refuse to align. To bridge this gap, theorists have attempted to modify dark energy or dark matter models, but these adjustments rarely survive the scrutiny of the actual data. Instead, researchers are looking toward a spatial solution known as the local void theory. This theory proposes that our region of the universe is abnormally empty. With less matter and less gravity to hold space together, our local pocket is free to expand much faster than the dense average universe. This accounts for both numbers. Direct observation yields 73 because it measures the fast-moving empty space immediately around us. The CMB yields 67.4 because it reflects the average density of the entire cosmos over billions of years. Reconciling our math may require us to accept that we live in a uniquely desolate, hollowed-out section of the universe. If we are truly living inside a massive void, we must ask what could have cleared out such a massive region of space. One radical possibility is the dual universe theory. It suggests our void is the result of a gravitational struggle between our universe and a second, unseen universe pressing against it. Under this model, the two conflicting numbers are the physical evidence of two different realities influencing the same region of space. Upcoming missions by the Roman Space Telescope and the Euclid satellite will soon map the boundaries of our region, hunting for the gravitational signatures of these cosmic borders. Ultimately, The Hubble tension provides a window into the structural limits of our universe, suggesting that we are seeing the influence of a much larger multiverse waiting on the other side.